Good day, ladies and gentlemen. Today we're going to be taking a look at some of the more common presentations, observations, and calculations we can do with exponential relationships. We'll be on page 73 and 74 of your pink packet, and we're going to begin with a skill that's going to ask you to write each exponential relationship in expanded form and determine the value of the expression. So for question number 1, where you have 3 times 4 to the 8th power, the expectation here is that you understand that the power of 8 belongs to the base of 4, and therefore we're multiplying 3, the initial amount, by 4 8 times. Go ahead and expand that. You can do that super quick. And hopefully you're showing that you have an understanding that we're multiplying 3 by 4 8 times. When you go to evaluate that in your calculator, the hope is that you're familiar enough with your calculator where you know where all the keystrokes are going to take place. So as we multiply 3 times the grouped quantity of simply 4 to the power of, that's our caret key below the clear sign, 8, we hit enter, and that tells us that we have 196,608. And there are other ways we could have evaluated that I'll show you in some of the other questions so that we're not repeating the process over and over again. And hopefully I can get through this video a little bit quicker. 196,608. In the second expression, ladies and gentlemen, where you have 18,000 times 2 to the times 2/3 to the power of 4. Once again, the expectation is that you understand that the power of 4 belongs to the base of 2/3. That's what's being repeatedly multiplied by the initial or original amount of 18,000. Because our value is between 0 and 1, it's a fraction, we're actually going to be doing repeated division in this multiplication process. So our initial amount is going to go down. Hopefully you're able to expand that. And when you do so, you show that you have 4 repeated multiplications of 2/3. And when you go to evaluate that on your calculator, you're able to perform the appropriate keystrokes by knowing how to identify the power key. 2/3, I often like to put it as a fraction in grouped quantity to the power of 4. Enter. And as I had suggested a moment ago, it is possible to do this in alternate ways. So you could have done 18,000 times 2/3. And you could have repeated that process times 2/3. And now it's stored in your calculator, and you could have hit enter 2 more times. And I'll round that to the nearest whole number amount. So we'll identify that as 3,556 to the nearest whole number. As you move on down, ladies and gentlemen, in Roman numeral 2, skill 2, we're hoping that you can identify the initial amount, A, that would be the value of the relationship at time 0, and the constant factor or common ratio, B, what we're repeatedly multiplying by over and over again in each of the expressions. In the expressions, ladies and gentlemen, it's important to understand the first letter of the alphabet, A, is what we call the first numerical quantity, and that is the value of the relationship at time 0. So in this instance, A would be 1,400 or 1,400, and B, the base of the exponent or the constant factor would be 9/10. And according to the instructions, we're asking you to evaluate that for the appropriate time or number of repeated multiplications in this instance when the exponent is 5. Therefore, you should show that in expanded form, and you can do that real quick, identifying that you understand that when we have 1,400 times 9/10 to the 5th, we've been multiplying 1,400 by 9/10 5 times. Once again, you can evaluate that on your calculator. There's several different ways to do that. And if we began with 1,400 and multiplied it by 0.9 to the power of 5, caret key on the right-hand side of your calculator, we hit enter. We can round that to the nearest, let's do this to the nearest hundredth as if it were money. So if this were money and we round it to the nearest hundredth, we would suggest that we have $826.67. We would look 69 cents, excuse me. We would look at the hundredths place, which was an 8 back to the 6, and the 6 would have told us to round up. As we continue on to number 2, ladies and gentlemen, my hope is that you're able to identify the numerical quantities that we call A and B as the initial amount of 100. If you don't multiply 100 by 1 and 25 hundredths at all, it's just 1 and 25 hundredths. The constant factor B is 1 and 25 hundredths, which represents a 25% increase in our initial amount. And if we evaluate it for 3 repeated multiplications of 1 and 25 hundredths, you could expand that and show that we have 100 times 1 and 25 hundredths 3 times. Several different ways to do that on your calculator, and as I promised, I want to show some of them in each of the different questions. So you could have suggested, Tooch, don't we have 100 times 1 and 25 hundredths? and 1 and 2500ths, and 1 and 2500ths. And that would have been an appropriate presentation, giving you 195 and 3100ths round to the nearest hundredth, or 3/10ths round to the nearest tenth. You could have also said, Tooch, isn't it 100 times 1 and 2500ths to the power of 3, and that would have been appropriate. If you follow order of operations, you could actually evaluate the exponent first, 1 and 2500ths to the third, and then you could multiply that by 100, and you'd get the same result. So there's many different ways to appropriately evaluate that relationship that are important and connect a lot of the math that you do throughout your entire mathematical career. Wow, we just did PEMDAS. That was cool. And rounded to the nearest tenth, that'd be 1 and 195 and 3/10ths. We would look at the tenths place, back to the hundredths, and the 1 would tell us to round down. As you continue on, one of the most common skills we ask you to do throughout exponential relationships, just like linears, is to be able to determine the relationship from a table of values. In order to do that, you have to understand that A, in the standard form of a exponential relationship, is the initial amount, the value of the relationship times 0. And B is the constant factor. They're the two most important numerical quantities in an exponential relationship. A you can often observe in the table. It'll be right in front of you. So we're seeing in this relationship that we have A. The value of the relationship at time 0 is 2. So we're able to quickly say that this table begins at time 0 with no repeated multiplications at an initial amount or value of 2. In order to determine the constant factors, some of you guys are really good and you can just see. You're like, Tooch, I know what's going on here. I see that 2 becomes 6, and 6 becomes 18, and 18 becomes 54. Aren't we just tripling? But often it'll be difficult to see. So you want to be able to formally determine the constant factor. Formally means with a formula. So in order to formally determine the constant factor, we want to divide each output value by its previous amount, or we say y2 divided by y1. We're going to undo the multiplication in the table by dividing. In order to do that, we would divide 6, the second measured amount, by 2, the first measured amount, and determine it's 3 times greater. And you can confirm that by doing each measured amount in the table beyond that by its previous amount. 18 is 3 times greater than 6. 54 is 3 times greater than 18. So the constant factor, or the amount that we're repeatedly multiplying by, is 3. This relationship can be written in y equals a plus b, a times bx form. You should be able to do that. Substituting 2 in place of a times 3 to the power of x. You can check that on your calculator super fast by just going to your table of values. If you have anything in there in your function, to your function list, clear out whatever you have and substitute in 2 times 3 to the power of x. Investigating your table. I should have reset my calculator. I'm going to have to reset let me reset the calculator real quick. Access to memory, choice 7 reset, scroll to all, enter, and then let me go back into my table of values once that's, my function list once that's done. So let's double check that 2 times 3 to the power of x is in fact equal to this relationship. And as I look at the output values, the measured amounts y, they go from 2 to 6 to 18 to 54, and that makes me pretty happy with my work. As you move down into question number 3, ladies and gentlemen, my hope is that you at least look at that table and you notice that as time moves forward from 1 unit of time to 5 units of time, that the measured amounts are going from 300 down to 18 and 7500. So this is a decreasing exponential relationship. With that, in order to write an exponential function rule, you would have to determine the two most important numerical values, a and b. A is the initial amount, the value of the relationship at time 0, which is a little bit weird because I don't see it in the table. And b is the constant factor, the amount that we're repeatedly multiplying by. Since I don't see A immediately, I can't observe it, I'm going to compute B. In order to compute B, I have to recognize that I would like to divide any amount in the table by its previous amount. I label the output values y1 and y2. First output value is 300, and second is 150. If I divide the second value by the first 150 by 300, it's only half as large. If I divide any amount in the table by the previous amount, they're only half as large as the previous amount. Therefore, we must be multiplying by 0.5 over and over again. That is our constant factor. In order to determine A, I'm going to have to either undo that multiplication of 0.5 with division, divide 300 by 0.5, or I'm going to have to rewrite the form or formula y equals a times b to the x and solve for A. Substitute in any point in the table. So I chose to write that y is 300 as a result of some initial amount multiplied by 5/10 to the power of 1 when x is 1. I divided out 5/10 to the first power in each side, and I determined that A was 600. I undid order of operations to solve for A. Once I knew what A was, I'm able to write an appropriate exponential function rule for this table. Hopefully you understand that that would be 600 times a half to the power of x. And once again, you can check that in your table of values on your calculator. For number 2, ladies and gentlemen, it would be a good idea to identify a and b on your own in just a moment, and then see if it matches up with the work that I'm able to produce on this end. See if you can come up with the appropriate function rule for number 2 on your own, using number 1 as a model. If you took a minute to pause the video, I think that a lot of you may be able to see this relationship without doing a whole lot of computations. But you should identify the initial amount A as 4. At time 0, the relationship measures 4. And you should notice that as we're moving throughout the table, it's increasing. It's increasing very rapidly. And we want it, that is because it's happening through multiplication. So we'd like to undo that multiplication with division. If we divide any amount in the table by its previous amount, in this instance, I divided 20 by 4, and I found out that it's 5 times larger. And that would be true throughout the rest of the table. If I divided 100 by its previous measured amount, 20, that would also be 5 as well. So the constant factor in this relationship is 5, and therefore we believe that this relationship is a result of 4 being repeatedly quintupled, multiplied by 5 over and over again, x number of times. And then we have a table that's more consistent with real life scenarios. We're investing money over time, and we believe that that is going, or according to the worksheet, that's going up in an exponential fashion, and we'd like you to compute that. So if you use the previous example as a model and you formally determine the exponential rule for number 4, or you should be able to formally determine the exponential rule for number 4. See if you can do that on your own. Give it a minute. Hopefully you took the time to investigate the table of values, ladies and gentlemen, and you've been able to determine that the initial amount was 100. At time 0, this relationship measures 100. Hopefully you computed the constant factor by undoing multiplication with division, and you identified an amount in the table, divided that measured amount by its previous measured amount to determine that it's 1 2/10 larger, and you're able to relate the relationship, the appropriate exponential relationship, as 100 times 1 2/10 to the power of x. I went ahead and checked that in my calculator to make sure that it was correct. So I went to my function list, and I typed in 100 times 1 2/10 to the power of x, and I computed the measured amounts throughout time to make sure that they matched the table that was given to us. Cool. Please flip. In Room numeral 5, ladies and gentlemen, we have skills very similar to what we just saw in the previous skill set. We're asked to create a function rule given a graph. And if given a graph makes you uncomfortable, you could extract out the information and make your own table of values. You could say, oh, what I'm actually seeing here is that at time 0, the relationship measures 2. And at time 1, it measures 4. And at time 2, it measures 8. And time 3 measures 16, and so forth. And you can make your own table. Through that observation, it would be really easy to understand that at time 0, we have a measured amount of 2. You could have just looked at your graph to determine that. That's the easiest way to determine it if it's available to you. And then you'd have to compute the constant factor b. To compute the constant factor b, some of you all see, you're like, doesn't 2 become 4 and 4 become 8 and 8 becomes 16? Aren't we just multiplying by 2 over and over again? Isn't this a doubling relationship? And it is. And if you saw that so quickly, you could have just identified the constant factor b as 2, or you could have computed it. You could have taken the measured amounts in the table and labeled them y1 and y2 for each point in time. It doesn't matter which pair you pick so long as they're consecutive, one right after the other. And if you divide any measured amount by its previous measured amount, you can determine how many times larger it is. In this case, they're all twice as large. Therefore, our constant factor b is 2 as well, and the function should be 2 times 2 to the power of x. We're starting with a measured amount of 2 and repeatedly doubling it over and over again. This shows up a lot in exponential relationships. The second relationship is a little bit more difficult to determine, and once again, you could make a table of values out of it if you're uncomfortable looking at it as a graph, but it's not necessary. What's happening in this relationship, and it's a little bit difficult to see what the initial amount A is. I believe it's 10, but I'm not positive. So you might want to write out your form or formula y equals a times b to the x, and choose to solve for b first. To solve for b first, you're going to have to undo multiplication with division. b equals y2 divided by y1. You'd want to label your measured amounts y1 and y2 appropriately. The first 2 consecutive amounts in the table, preferably, but it doesn't have to be. And you would want to divide the second measured amount by the first measured amount to determine how many times larger it is. If you were to do that on your calculator, you'll find out that it is 1 25/100 larger. That is our constant factor b. Now, once you have b, if you're not certain what a is, you could have computed it. In order to compute the value of a, you'd have to rewrite your formula y equals a times b to the x, and you would substitute in any point from the table. I usually choose the first point because the numbers are the lowest or easiest to work with. So I knew that y was 12 and 5/10, and that was equal to a, which I was uncertain of, times b, which we just computed, 1 25/100 to the time or power of 1, because x was 1 at that time. When I divide both expressions by 1 and 25/100ths, I'm able to determine that A is 10, which was kind of observable, but I wasn't sure. Once I have those two numerical quantities, I can write out the relationship for this exponential function. And hopefully you chose to write that we're starting with 10 and multiplying by 1 and 25/100ths to the power of x. In the third table, ladies and gentlemen, all those relationships are true, and just for the sake of keeping this video as brief as possible, my hope is that you understand that this relationship is decreasing throughout time, it's going down, and that you're able to identify the initial amount as 40 or compute it if you needed to. You might even just be able to recognize that we're going from 40 to 20 to 10 to 5 and say, Tooch, aren't we just multiplying by a half over and over again? And we would be. And therefore, we have 40 multiplied by a half over and over again to the power of x. Down below, the last skill that we often ask you to do as we work our way through this unit is identify one of the four major relationships we spent a lot of time studying so far this year. You were in the exponential unit, y equals a times b to the x, or the repeated multiplication patterns unit. We began the year in a linear unit, y equals mx plus b, that's repeated addition. Quadratics are x squared relationships, they make u's. We'll spend a lot more time with those. And absolute value of x makes a v. In order to determine which of those four types of relationships you're looking at in the table of values, you need to observe the outputs. So the expectation is that you would take the time to look at the y column and see how the measured amounts are changing throughout time. From 5 moments of time ago to 4 moments of time ago, the first relationship increases by 3. Then it continues to increase by 3 till it gets to a measured amount of 6, and then it decreases by 3. Because we have an inverse constant rate of change or amount of change, that's going to mean that it's an absolute value. This relationship reaches a vertex. There is symmetry or sameness on both sides, so we know that it's going up then coming down, and it's going up in a linear pattern, up 1 over 3, up 1 over 3, up 1 over 3, then going down in a linear pattern. Because it's two straight lines that meet at a vertex, that 100% means this is an absolute value. When you get to the second table, g of x, as you begin to investigate the outputs to see what the pattern and the measured amounts are, you notice that it increases by 6. Then it goes from 7 to 9, and there's an increase of 2 in that interval of time. It then decreases by 2, decreases by 6, and decreases by 10. This, ladies and gentlemen, is a relationship that also has a vertex. If you look closely at the table, it goes up to a maximum amount of 9, and then it comes down. So we see symmetry or sameness on both sides, which usually indicates an absolute value or quadratic. And because we have a non-constant, not the same, inverse rate of change, that's going to mean that it's quadratic. It's a second-degree polynomial. Also, we should notice that our measured amounts, if we take the second difference, the difference of the differences, from 6 to 2 is a decrease of 4. From 2 to negative 2 is a decrease of 4. From negative 2 to negative 6 is a decrease of 4. And negative 6 to negative 10 is also a decrease of 4. Because our second difference is the same, that means this is a second-degree polynomial and therefore a quadratic. As you move on down the page, ladies and gentlemen, I'm going to go to p of x next. And in p of x, as we investigate the output values of the pattern of the measured amounts, we notice that this relationship decreases by 2 from 5 units time ago to 4 units time ago. From 4 units time ago to 3 units time ago, the measured amounts go from negative 3 to negative 5, a decrease of 2. And it continues to decrease by 2 over and over again. This is a constant rate of change, and because the rate of change is constant, or amount of change, say constant amount of change, this is a linear pattern. Lastly, as we take a look at the final relationship, h of x, when we investigate the output values, we notice that they increase by 2, then they increase by 3, then they increase by 4.5, and then something else. But, by 2, by 3, by 4.5. It's a little bit difficult to see if there's any pattern going on there. And you might even check the second difference. Tooch, if I go from 1 to 2, I'm going up by 1. If I increase from 3 to an increase of 4, I'm increasing by 1.5. And it might not be obvious what's happening here. The first difference doesn't seem to have a pattern. The second difference isn't the same. So because it's not a result of some form of repeated addition or pattern with repeated addition, there's a good chance it's a result of repeated multiplication. Y equals a times b to the x. If it were a result of repeated multiplication, there'd be a constant factor b. The difference, if we undo multiplication with division, we should get the same multiplied amount throughout the table. That would require us to label our points y1 and y2, or our measured amounts, and to divide 6 by 4 to begin with. Then to divide 9 by the previous amount 6, then to divide 13.5 by 9, and see if those amounts are constant. To do that, I would go to my calculator, and on my home screen, I would divide 6 by 4. I would divide 9 by 6. I would divide 13.5 by 9. And what I notice is they are all 1.5 times greater. Therefore, because I'm getting a constant factor and we're repeatedly multiplying by the same amount over and over again, that proves that this is an exponential relationship. This was a review of what a lot of the work we've done in exponential relationships. You're often asked to identify what type of mathematical pattern we're looking at, whether it's linear, quadratic, absolute value, or exponential from a table of values. We see that a lot. Many times you're asked to make an equation from a graph, given a graph. Often we have you write a linear equation or a pattern, or an exponential. Sometimes we'll have you do a quadratic as well. Many times with exponentials, we'll give you a table of values as discussed in that final skill, and we'll ask you to come up with the repeated multiplication pattern. We'll often ask you if you can identify the components of an exponential relationship, if you know what the initial amount are and or the constant factor b, and we will most certainly ask you to expand and or evaluate them. This is a review of exponential relationships. I hope most of that makes sense, and I'll see you all in class. Take care.